Hi guys, this is Jad Hussain again with a new video. In this video we are going to design an underground water tank. As you can see in this figure, this is the plan, and this underground water tank will be having dimensions like outer to outer dimension in x direction or in this direction will be 4800 millimeter, and in other direction it will be 3900. The wall thickness is 300 all along. The section is shown like this. The base slab will be 300. The height will be 3300 clear height, and the top slab will also be 300. So total height of the wall will be 3600. So we will be modeling this at the center of the walls and center of the slab. Let's start. New project, space, underground tank. Let's select the units in millimeter, Newton. Next, yeah, finish. Let's close this one. We can use wizard. Very first thing is to confirm the units. The units should be millimeter. Let us select the model. It will be surface or plate model, and it will be the quad element. Let us first model the base plate. The base plate will have coordinates 0, 0, 0, and then 4, 5, 0, 0, then 4, 5, 0, 0. Of course here it will be 0, and in z direction it will be 3, 6, 0, 0. Here it will be 3, 6, 0, 0. Here it will be 0 and 0. All these units should be in millimeter. Quad element, apply. Sorry. We have to divide this into finer mesh. Let us divide this into 30 elements, this into 24, 30 and 24. Let's apply. Okay, let's merge. Fine. Save. Similarly, we can construct the wall. Let's see the units. Millimeter. Quad element, units are in millimeter. The wall on one side will be 0, 0, 0, then 0, 3, 6, 0, 0 and 0, then it will be 4, 5, 0, 0, y will be 3, 6, 0, 0, and the last point will be 4, 5, 0, 0 and 0 and 0. So it will be divided into 24, 30, 24 and 30 segments like this. Let's merge. Yes, yes, no problem. Let us save. We can add the side wall. Similarly, units, select unit, millimeter, quad elements, and these are 0 0 0, then 0 3 6 0 0 0, then 0 3 6 0 0 3 6 0 0, then here it will be 0 3 6 0 0. All sides are 3 6 0 0, so their divisions are 24 24 24. Units are in millimeter. Apply. Let us merge with the model. Yes, no problem. So here the walls are created on the two sides. Now we can copy and paste or translate, either way it is possible. Let us select the walls, the plates which are parallel to XY. We can copy and paste. So this is the point where we will paste. Okay, so here it will be pasted over here at a distance in X direction at 4500. No, something wrong. Let's cancel. We have to paste here. See the reference? Yes. So it will be pasted at a distance of 3600. Yes. Done. Save. Now we can select the walls which are parallel to YZ, and we can translate in X direction at a distance of 4500. Yes, done. So this model is done. If you remember in this figure, the base slab is projected out, so 300 is out of the slab, 150 over here. That means 450 on this side, 450 on this side. So on all sides it will be projected 450 millimeter. Let's select the base, all plates parallel to ZX. Let's view the selected one. So what we have to do, we have to copy these plates, because one plate has a width of 150. So we can copy and paste these three plates on this side. Copy, paste plates. Let's see the reference point. Yes, it is correct. Okay, let's say the dimension, inner dimension is here and here. Okay, so same thing we can do over here. Paste plates. See the reference point. Now we want to select this point as a reference point. and here. Okay, so this side is done. Save. Now we have to select these three lines, copy, paste plates. We have to select this point. Okay, minus 450, that's fine. So it is done. Same thing we can place over here. See the reference point? No, our reference point should be this one, and it should be placed over here. Yes. So now if we see the whole structure, it will be like this. I'm not going to model the top plate for the time being. We can model that one with a opening in the top plate as a manhole. It can be done later, but okay, let's see for the time being this one. Now what we have to do, we have to select all plates and assign a thickness. We know that the thickness of the plates 300. Let us assign. Close. Okay, I don't want to see. Let's see the rendering. Yeah, perfect. So this model is complete. And now we have to apply the loads. Let's apply the loads. First, let's apply the dead load. Okay, this is the dead load. Add. Let's add. Yeah. Add. Assign to view. Yeah. Let us save at this stage so that if we do some mistake, it will be easy to start from this point. Now we will design this with a concrete strength of 32 megapascal. Of course, the yield strength of the steel will be 60 ksi or 404 megapascal. Density of concrete is 24. Soil density is 18 kilonewton per cubic meter. Internal fraction angle is 30 degree, and allowable bearing capacity is 200 kilonewton per meter square. K is calculated as this 1 minus sine 5 over 1 plus sine 5, which comes out to be 1 by 3 or 1.33. This is the height, and the pressure at the bottom. This is the soil pressure at the bottom rather. Soil pressure at the bottom of the wall. This will be 7.2 kilonewton per meter square. And we assume that there is no subsoil water. It's very deep. So we will not consider the presence of subsoil outside the tank. Coming back to the tank, let us add the live load, which is the water inside the tank. Let's see, this load is considered as live load. Add. Okay. Let's assume that the water is full. So water can reach up to 3.3 meters maximum. So multiplied by the density, which is 10 kilonewton per cubic meter, multiplied by 3.3, it will be 33 kilonewton per meter square at the bottom. So let us select the base plates parallel to ZX. Select, view only the selected elements. Let's see. So we have to apply the water pressure only up to here. So we have to add plate load, full pressure. Sorry, one more thing I should do, change this to kilonewton per meter square. It would be very easy for me. Okay, no problem. So let us change the unit, meter, kilonewton, right. So let us add the load, plate load. This is, it was 3.3 multiplied by 10, 33 kilonewton per meter square. It will be in local z direction. I am not going to put a negative sign. Add, and let us select the plates. I am not going to okay, and I'm going to cut only this much. Okay, so I'm going to associate this pressure only to these plates. Let us see in 3D. Okay, so the load is acting downward. Fine. Now the pressure of the water will be a triangular distribution of water pressure on the walls. So how to apply this triangular distribution? Let us first select the wall. Let's first select this wall. Okay, so we can select only these walls. Fine. Okay. Let's see what is the orientation of the element. So the plate orientation is like this. So x is upward, y is in right hand side, and z is in this direction. So z positive is in this direction. So that means if we want to apply water pressure from inside, then it should be positive. Okay. So let us add plate load, hydrostatic pressure. Let us select the plates. All plates are selected. Oh, sorry. It will not reach up to the top point. Close. Let's do again. Add plate loads, hydrostatic. Let us select the plate. So this pressure will be from here to here. Done. Now the pressure at the top will be 0. So WT will be 0. Pressure at the bottom will be 33 kilonewton per meter square, and it has to be interpolated in y direction, global y direction, and we saw that it will be acting in local z direction. Close. So now you can see that the load, a triangular distribution of pressure is there, and this load is acting from the inner side of the tank. Let's see the whole structure. So this is the correct sense. Now we can select the other side of another side, this one. Okay, so this is, we have already selected. We can select this wall. View selected only. We can select wall parallel to XY plane. View select only. So the base slab plates are gone. Again the same thing, we have to confirm what is the local coordinate system here. Let us zoom. So the local coordinate system x, y and z. Z is inside. That means if we want to apply pressure outside, we have to add here a negative sign, right? Okay. Add plate load, hydrostatic, select plates. Let us select these plates. Done. We know that it will be minus 33, 0. This interpolation should be in y direction, local z. Okay, add. Close. Let's see. So that means water pressure on both these sides are applied correctly. Okay, fine. Let us save. Now select the other two sides. Select walls parallel to YZ. Let's view the only selected elements. Let us select one side first. Selected only. Let us see the plate orientation. So this Z is going in this direction, positive. That means we have to apply a negative pressure over here with minus value. Add plate load, hydrostatic, select the plates, done. This will be 0, this will be minus 33, interpolation along Y, local Z, that's fine. Add. Close. So this is the correct direction. Oh, I did a mistake. Anyway, no problem. I have applied this from the top. That's okay. Now we have to select this wall. Again, select walls parallel to YZ. Selected only. Let us select only this one. Now the same thing, we have to confirm the orientation of the plate. Z is outside, so here the pressure should be +1. So let us add the pressure now. Add plate load, hydrostatic, select the plates, done. This will be negative 33. Sorry. Close. Let's confirm once more. Plate orientation. Let us see by zooming this one. Small portion should be. magnified. So this Z is in this direction, so it should be positive, not negative. Okay, add plate loads, hydrostatic, select the plates, done. So y1 should be 33, this should be 0 in y direction, local Z, add. Close. Now you can see how trapezoidal load is applied over here. Actually, I have to apply the soil pressure from outside, but let us for the time being leave it as it is. The main purpose was how to apply the trapezoidal load. So this is the way we apply trapezoidal load. That means this water pressure and the soil pressure can be applied like this. Now let us define the support conditions. We know that the bearing capacity is 200 kilonewton per meter square. Let us select plates parallel to ZX. Now we have to specify support conditions. Of course, this is foundation, but what type of foundation this is? This is elastic mat, and the modulus in y direction. Normally, a thumb rule says that the modulus is a modulus of subgrade reaction is 120 times of the bearing capacity. That means 120 multiplied by 200, this comes out to be 24,000 kilonewton per cubic meter. 24,000, add, let us select plates parallel to ZX. So let us assign save. We can define the load combinations. Let's say 1.2 dead, 1.6 live, add. Then we have to add perform analysis command. Okay, let us save and let's see what happens when we run this model. No error, no warning. It's okay. So now we can enter in design of concrete. We can define F-C. It should be 32,000 kilonewton per meter square. That to assign to view. Yes. And then we have to design slab. Add. Assign view. Okay. The rest is fine. Let's analyze. Yes, we have to save. Let's see the output file. Now this output file gives you result in this format, like longitudinal reinforcement, its moment, transverse reinforcement, and all the elements are listed over here. If we go to post-processing, okay, now I don't want to see the supports. Let's just select base slab. Let's view only this one. Now results, what we want to see is this stress contour for this one, and we want to see the base pressure. Apply. Now the units are in PSI. Let us change the units. Force units. Yes, there should be kilonewton per meter square. KPA. Or there is kilonewton per meter square. Apply. Now we can see that the maximum pressure here is 82 or 84 kilonewton per meter square. Our bearing capacity was 200, so this is safe. And then we can interpret the results to find the reinforcement which is on this face and on the other side. Normally 300 millimeter thick slab, it will need only the minimum reinforcement as per the code, and that is confirmed from our result over here. Everywhere only minimum steel is required. Only minimum steel is required. So no issues. We can use only minimum reinforcement. Now so far I am going to stop my model over here. Maybe in next session I will add the soil load from outside, and then we will run it again and we will try to interpret the result and try to calculate the reinforcement. Hopefully you like this video. Please do not forget to subscribe my channel. Thank you very much.